Right. Good afternoon, everybody. Um, Welcome back. Glad you hope you had a good break. Um, 1 second. Quick. Okay. All right. So we have we're gonna actually start a new topic to talk about the Dalton's Law, partial pressure, and then the ideal gas law. And then after we do that, if there's time, we're gonna start talking about atomic structure and light. Um, Let me share my screen. And this handout, you don't have this yet. Well, you got uh, you have the partial pressure handout because that's already on Blackboard. But you do not have the light and atomic structure handout. But I'll post that today um, when I post the video and the notes and all that stuff. I'm just waiting on this to load up.
I have a quick question.
Go ahead.
When is our final?
Oh, I don't know. I have to go back and look. I sent a schedule, a calendar, in one of the most recent announcements with the date on it. But I'll have to go back and look at that. But
Okay, thank you.
I definitely sent the date out already. This last day of class is Monday. I think it's May 2nd, May 1st, I think, something like that. If you go to Blackboard and pull up the announcements, you'll see there's like a table in there that I sent out, and our class is highlighted with the date and time.
Okay, thank you. I'm gonna go check.
All right. Yeah, good question. So I'm going to actually the lab final I'll post this week, and you'll have between now and I think I'll leave it open for like a week, but I'll handle all that. You'll get an announcement about that. That lab final is going to be on Blackboard, and you just go in and take it. And I'm probably going to open it on Thursday. Yeah, thank you, Mary. I see it May 2nd, 10 to 12. And that's going to be, we're going to discuss that in a little bit more detail as far as the final. I have a couple of things that I want to talk to y'all about, but not today. Maybe on Friday we'll discuss it about that, the date and the time and the format of the final. But we'll talk about that on Friday. All right. Yeah, but the lab final itself, I'm probably going to post that today or tomorrow. More than likely tomorrow because I had a long to-do list for today. But I'll probably post that lab final tomorrow and then just leave it open until what's tomorrow, the 21st. So I'll leave it open through the 28th. And you'll get an announcement about it. But you'll get that. That'll be this afternoon when I send that out. All right. So we're going to start talking about Dalton's Law, partial pressures, and we're going to connect that to what we call the ideal gas law. So we're going to talk about and so we're going to talk about the ideal gas law as well as Dalton's law of partial pressures. Give me 1 second. Grab. All right. So what Dalton's law is dealing with again, partial pressures. And basically what it says is that if you have a mixture of gases, um, the total pressure of that mixture is the sum of the partial pressures of each of the gases, right? So we have a, right here, we have a generic mixture. P total is PA plus PB. But let's say we have a gas that is a combination of nitrogen, oxygen, and chlorine. All right. And so these gases make up this mixture, but each one has its own specific pressure, right? So that's what makes this kind of a special case, is because each gas that makes up the mixture has its own specific partial pressure. Right. And so those partial pressures, we label them, or we indicate them as, like for nitrogen, we'll say the partial pressure is P subscript N2. And then for oxygen, we'll say P, and then with a subscript O2. And then for chlorine, PCl2. Right. And what Dalton's law says is that if we take all of those pressures and add them up, we get a total. So it'll be PN2 plus PO2 plus PCl2, right? So anytime we have a mixture of gases, each gas has its own partial pressure. And because of that, if you add up all the partial pressures, then you're going to get the total pressure of a given gas, right? Along with that, we have what's called the mole fraction. All right. And so we have what's called a mole fraction, because each of those gases is in a specific amount. And so there are going to be a certain number of moles of each gas. So what the mole fraction is the fraction of gas molecules in question, right, that make up the molecules in the gas mixture. So if the partial pressure is composed of the total pressure of each gas, the mole fraction, which is really just a percentage, would be the moles of one of the gases divided by the total number of gas, or the total number of moles of each gas. So for our example, the mole fraction, let's say for chlorine, would be, right, the moles of chlorine divided by the total moles of the of all the gases combined. All right. So moles of chlorine divided by total moles of combined gases. So that mole fraction is going to come into play later, because we can take the mole fraction and the partial pressure. You know what? Sorry, that was my mom. She never remembers my schedule. I always tell her when I have class, but she never remembers. So, but we can take the mole fraction and relate it to the partial pressure in this equation right here. Right. So the mole fraction is the or the partial pressure can also be determined by the mole fraction times the total pressure. We're going to do an example that actually illustrates this. So the mole fraction is like, it's the mole fraction times the total pressure can also give me the partial pressure. There's another way that I can determine the partial pressure of a gas, and that's using what we call the ideal gas law. I'm just gonna know how to write it out first. Right. And so with the ideal gas law, the way that we look at this is the pressure times the volume is going to be related to the number of moles times R times T, right? And I'm gonna give you what each one of these terms means. So P obviously is pressure. V is volume. N is the number of moles. R is the gas constant. That's a known value. And T is the temperature in Kelvin. All right, so the partial, you can also determine partial pressure that way and using the ideal gas law. So you can determine the partial pressure of any given gas within a mixture by using the mole fraction and the total pressure, if you know the number of moles of each gas, or you can determine it using the ideal gas law, which is PV equals nRT. All right, so the ideal gas law takes, it makes some assumptions that a gas is behaving ideally. So it makes the assumption that all of the collisions happen between the gases with no loss in energy. It makes the assumption that the volumes are negligible. It makes the assumption that the gas particles all have equal size. And it also makes the assumption that gas particles are moving randomly. So with all that said, we're able to apply the ideal gas law by making those assumptions. All right. So let's take this and let's look at a couple of examples. And let me refresh this here too, because you may or may not remember this from when we talked about it. This is 273 plus Celsius. That's how you get your temperature in Kelvin. All right. So if you're given a temperature in degrees Celsius, you can calculate that in Kelvin by adding 273. All right, let's take this example. I want to actually put it on a different page because I want to show the calculations, then we'll come back to them. All right, so notice it says calculate the partial pressure of an air sample. So it's telling us what we're working with. That contains 0.76 grams of N2 and 0.24 grams of O2. When the volume is 1 liter, and then the temperature is 20 degrees Celsius. So before we do anything with this, and let me change this because this should be total pressure. Before we do anything with this, we need to make some conversions. So that we can work within the confines of what we know. So the total pressure is always going to be P total, the sum of the partial pressure. So P N2 plus P O2. All right, so when we know that, then we're able to now figure out what PN2 and PO2 are using the numbers given. And we can do that using the ideal gas law. So PV equals nRT, and we're going to do it for each one. So we're going to calculate P for both nitrogen and oxygen, right? So let's do that. So let's solve for P. So we're going to divide this by V and divide this by V. So P N2 be N RT over V, and then PO2 is going to be the same, N RT over V. And then these numbers we're going to plug in, right? In order to get the number of moles of nitrogen and moles of oxygen, if we start out with grams, we need to convert that. So first we need to convert grams to moles, and we need to convert degrees Celsius into Kelvin. Let's do that one first. All right, so Celsius to Kelvin is easy. We take the 20 degrees Celsius plus 273, and that's 293 Kelvin, no problem. For grams to moles, we have 0.76 grams of, so let's go, 0.76 grams of N2 divided by, so for nitrogen, you have 2 atoms and each one is 14 grams per mole. So there's going to be 28 grams per mole. We can never get away from this. Grams are going to cancel. And then we're going to be left with a number for mole. Somebody can calculate that. And then for oxygen, it was 0.24 grams. And it's going to be divided by 32 grams per mole. All right. And the reason it's 32 is because you got 2 oxygens and they're both, the atomic mass is 16 grams per mole. All right. So we're going to say 0.76 divided by 28. That's going to be 0.0271 moles. And then we're going to say for the oxygen, 0.24 divided by 32. So it's going to be 0.0075 moles. So now we have our moles, we have our temperature. The only thing that's left is R, the R value. And let's talk about that. So R is what we call the gas constant. And the fact that it is a constant means you will never have to calculate it. It's always a given value. That R value changes based on the units for volume and for pressure. If the volume is in meters cubed, so volume and pressure units change, then there are different R values for that. If the volume is in meters cubed, then the R is going to be 8.2057 meters cubed atmosphere per mole Kelvin, right? So meters cubed atmosphere per mole Kelvin. If the pressure is in torr, because your pressure can be in, there are multiple units for pressure as well. We're going to talk about that too. But if the pressure is in torr, then R is 62.36 0.37 liters torr per mole Kelvin. Yeah, and if also that pressure is in millimeters of mercury, then it's the same number. Per mole Kelvin. Right, so R can change based on what your units are. So pressure is in torr or millimeters of mercury. You can use these numbers. If the volume is in cubic meters versus liters, you can use this number. So with that being said, now we have everything we need to solve for P for each one of these. So let me add another page in right quick. All right, so we can plug these numbers in. So let's do the P for nitrogen, partial pressure for nitrogen. N we know is here. So I'm going to put that number in, 0.0271 moles. And then R, since the pressure is given as, well, we're looking for the pressure, but we're going to use the standard R value, which is, let me put it here. So when the pressure is in atmosphere, let me see. I'll just move this up. So when my pressure is in atmosphere, I can just use the standard R value, which is 0.0821 atmosphere liter per mole Kelvin. All right, so we're gonna use that for R. So I have my moles. I'm gonna put R here, 0.0821 atmosphere liter per mole Kelvin. And if you notice, this is going to be set up for everything to cancel. Shrink that a little bit. So N, R, and T go on the top. It's 293 Kelvin. And it's going to be divided by V, which in this case is going to be 1 liter. Right, so you can see right away, moles are going to cancel. Kelvin will cancel. And liters are going to cancel. And we're going to end up with the pressure, the partial pressure for nitrogen in atmosphere. Going to be P N2, which is going to be 0.65 atmosphere. All right, and we can do the same thing for oxygen. We already calculated the number of moles, and again, this is the relationship that we're using. So the number of moles for oxygen we calculated to be 0.0075. So we put that in. And then we're going to use that same R, 0.0821. And again, that's atmosphere liter per mole Kelvin. And then the temperature is going to stay the same, 293 K. And all that divided by the volume of 1 liter. And again, all of your units are going to cancel with the exception of atmosphere. So we will cancel everything out. Moles are going to cancel, liters are going to cancel, and then Kelvin will also cancel. And we're left with atmosphere. So for that number, it is 0.18 atmosphere. So the question, let me go back. I'm sorry for all the pinching, but the question says to calculate the total pressure of air sample. That's 0.76 grams nitrogen, 0.24 grams of oxygen, and at a volume of 1 liter at 20 degrees Celsius. So the total pressure is going to be the sum of these two. So P total is going to be PN2 plus PO2, which is 0.65 plus 0.18, which is 0.83 atmosphere. That's the total pressure. All right. Any questions about that? So what we did was we took that ideal gas law and we treated each one of those gases separately to find their partial pressures. And in doing so, we're also able to find the total because we can just take the partials and add them up, add them together. All right. And then there's the second part to this question. Let me go back up. Any questions before I move on or scroll up or do anything else? All right. So let's go back to here. And it says, and it's talking about the same sample here. So it says the sample of air is heated until the total pressure is 1 atmosphere. What are the partial pressures of the two gases? So let me put another page in and paste that down here. All right. So with this example, the pressure is 1 atmosphere total. So that's the sum of all your pressures. So now you have a new total pressure, and it's asking what the partial pressures for the two gases are. Right. And so this particular part of the example, we can apply the other relationship. We know the ideal gas law relationship. We've already done that. But now we can also apply the mole fraction. Right. Remember, the mole fraction will be XO2 plus X N N2. That's the total number of moles. Right. So the mole fraction would be if I want to find oxygen, it's going to be XO2 over the total. If I want to find nitrogen, it's going to be XN2 over the total. And we know the total number of moles, right, of each one. We know that from this example, there are 0.0075 moles of oxygen and at 0.0271 moles of nitrogen. So let's find out what the mole fraction for each one is. So X for oxygen is 0.0271. Hope I remember that properly. No, that's nitrogen. And then for oxygen, it is 0.0075. Right. So now we just need to figure out what the fraction is. So let's add those two numbers together. So 0.0271 plus 0.0075. The total here is 0.0346. And then the fraction is going to be 0.0075. This is for oxygen. And then 0.0271 over 0.0346. And this is for nitrogen. All right. All right. So when we calculate that, we'll see that the mole fraction for oxygen is 0.2174. I'm going to go ahead and calculate it. So 217. Mole fraction of oxygen is 0.217. And then for nitrogen is going to be 0.783. So those are our mole fractions for each one. Right. And so now we can just take the mole fractions. If you remember the relationship between total pressure and mole fractions, it's the mole fraction times the total pressure equals the partial pressure. So mole fraction of O2, and then the same thing, mole fraction of N2 times total pressure equals the partial pressure. So we could just put those numbers in. The total was given as 1 atmosphere. So when we heated up this canister of gas, the pressure increased to 1 atmosphere. Right. So now we can just say, and it's going to be the same number, right? It'll be 0.217. Yeah, 217 times 1 atmosphere, and then it'll be 0.783 times 1 atmosphere. Right. And because the pressure is 1, you're going to get the same number. So the partial pressure for oxygen and for nitrogen for this example is 0.217 atmospheres for oxygen and then 0.783 atmospheres for nitrogen. Right. But the question gave us, it says a sample of air is heated until the total pressure is 1 atmosphere. And what are the partial pressures? So we have to remember the relationship between the total and the partial pressures, which we said the total is the sum of all the partials. And then the mole fraction, which is the number of moles of each gas, is if you multiply that by the total, you can get the partial that way too. So that's 2 different ways that we looked at for calculating partial pressures. So let's do one more example, attacking this just kind of like a slightly different way, but let's do one more example. Page in the wrong place. All right. Let's do another example. Let's say we have another air sample that's composed of 78% N2, 20.095% O2, and 0.95% of argon. And the question is to calculate the partial pressure of each gas in the sample. And this is at 760 torr. So 760 torr is actually a conversion. 1 atmosphere is 760 torr. But we can actually leave this in torr. It's fine. So what we'll do in this case is, first of all, we'll assume a 100 gram sample, right? And if that's the case, then we can use the percentages really as mole fractions. Because if we say that there's 100 grams of this gas, or we say that there's 100 moles of it, of this, the total 100 total moles in the mixture, then we can assume the percentages as mole fractions. Right, so let's do that. Let's say that 78.08% N2 is the same as 0.7808 moles of N2. Right, and by the same token, we'll say that the 20.095% O2 is the same as, and this is something we've seen before. We've done this when we were doing percent composition. Right, and then the 0.95% of argon, we can say is 0.0095 moles of argon. Right, so now we know if we use those as mole fractions, we can just apply what we just did, which is to take the mole fraction for each one. So xN2, xO2, and then xAR times the total pressure, which is 760 for each one. Right, so we just plug those numbers in. Right, and we know that this number is 0.7808. This number is 0.20095. And this number is 0.0095. Right, and if we multiply each one of those, then we'll get the fraction of that, the partial pressure of each gas using that fraction. So let's see, 760 times 0.7808. So this is 593 torr. Let's say 593.41. And then, of course, it has to add up to 760. So 0.20095 times 760. This will be 152.722. torque. And then 0.0095 times 760 is 7.22. Right. So this total should add back up to 760. Right. So that's another way to apply the partial pressure. If you're given percentages, as long as they add up to 100, you can assume that, and they have to add up to 100, but you can assume that from the percentages, you could take those as the mole fraction. Just turn them, just like we did. We were doing percent composition, and we were also doing percent abundance, right? So when you have a percentage, you can always turn it into a fraction. And if you have a fraction and a total pressure, you can determine what the partial pressure is. All right. Questions? Any questions about any one of these examples that we've done so far? All right. I don't want to introduce light because I only got 4 minutes. I actually went a little bit longer with these examples than I did in the earlier class, but that's okay. What I'll do on Friday is we're going to introduce light and discuss the different characteristics of electromagnetic radiation, and then talk about the energy of a photon, how to determine the energy of light. And really, we only have that and 2 other topics to cover: electron configuration, which we could do in a half a class, and then Lewis structures, which we're going to do also. So I'm going to stop here, and then we'll pick this up on Friday.